Hello, welcome to my talk, Rethinking Software Testing for Data Science. Imagine you are working on a data science project and you get a new development machine that only has the operating system installed. You get the raw data for your project and you get your code. How much time is it going to take you to reproduce the results that you reported previously? Ignore the time that it takes for your code to process the data. Just take into account the time that it takes for you to maybe install dependencies or do any manual steps involved and start running your pipeline. If it takes you more than 5-10 minutes, there's a lot of room for improvement. Now, take into account that processing a data set that has been modified doesn't count as reproducibility because your analysis goes from your raw data all the way through the final output. Since any change that we introduce to our project has the potential to break things, we should be testing our code for reproducibility every time we make a change. But this is not practical, because it means that we have to spend time checking things every time we introduce a change. And this idea of testing software is not new. And we should be writing a different program that automates this process for us. And this is what software engineers do every day. They automate the process of testing software. This talk is about software testing, but from the data science perspective. We are going to introduce the principles of software testing. We are going to also speak about the challenges that we face when we want to apply these principles to data science and how we solve these problems. We cannot simply apply the regular procedure because data science projects have specific characteristics that we have to take into account. We're also going to speak about some debugging strategies. How do we go about fixing problems in our projects and make sure that these bugs don't come up again? And we're also going to mention some tools and resources so that you can start applying these principles in your projects with open source options. What's the standard software testing procedure? It goes like this. A programmer introduces a small set of changes to a project. Then they save the changes. And if you are using a version control system like Git, this means creating a new commit. Then your tests are executed. You wait for the results to come back, and if the changes didn't break anything, it means success. If any of the tests didn't pass, it fails. And the idea is that if all your tests pass, you can move on and work on something else. If your tests didn't pass, then you have to revisit your changes, fix them, and try again. Which are the benefits of automated testing? The first thing is that we can quickly be notified when we break things, and that's great because we make sure that as we make changes, we are always keeping things working well. Since we are introducing small changes, we can also pinpoint errors to specific lines of code. It's much easier to find an error in 20 lines of code than 200 lines. And overall, this speeds up the development cycle because even though we are writing another program to test our original program, it allows us to repeat this cycle very quickly about introducing changes, testing, then checking for results. One important thing to keep in mind is that for testing to be effective, results have to come back quickly because we have to wait for the tests to be done to make a decision of continuing or revisiting our changes. Now, data science has some challenges when we want to apply these principles. And this is very important because we cannot simply apply the standard procedure that I explained before. The first challenge is coming up with good test cases. When we are testing software, we want to test with representative inputs of things that we want our code to cover. For example, if we are testing a traditional piece of software, maybe an e-commerce website, we may have a function that logs in users. Well, we can come up with some test cases like what happens if I pass the wrong combination of user and password. These kinds of things come up naturally. But in data science, we usually have functions like get data, clean data, transform data. It's not so easy to come up with good test cases for these types of transformations, these types of functions. The second challenge is structure. Since our analysis has a predefined order, we get the data, then we clean it, then we transform, and we have to do it in that order. We have to take that into account when we want to test a software that has this kind of structure. The other challenge is speed. If we are dealing with big data sets, our pipeline may take a lot of time to run, but even with small data, if we are using complex algorithms, the processing time might be long enough that we cannot run our pipeline every time we introduce a change. And finally, changing data. Even if we follow all these recommendations, if the data that we are using as input changes, this has the potential to break our code. So we have to keep that in mind. Let's speak about the first challenge, testing data transformations. The first question that we should ask ourselves when we are testing a piece of software is what can go wrong? Imagine we are working with user streaming data, people listening to songs, and we have three columns, the user ID, the timestamp, and the song genre. As we start doing some exploratory analysis, we start to build a picture of how the data looks like and what are the properties. Maybe we were assuming initially that we always have a timestamp, and then we find that sometimes the timestamp is missing. Or we may be assuming that the song genre is always a rock, pop, or jazz, and then we find some rows that have unknown. It's not a missing value, it's actually the string unknown. But we cannot spend all our time doing exploratory analysis. At some point, we have to move and start doing other things. The important idea is that all these expectations that we have about the data, we should make them explicit. And when I say explicit, I mean writing a piece of code that checks those expectations. For example, if we are assuming that we should always have a user ID because that's implicit in our code, well, let's make that expectation explicit before we run that piece of code. So we write this test that checks that we always have a user ID. If our code is assuming that we only have rock, pop, and jazz, let's make that explicit and test that what goes into that piece of code only has those values, that it doesn't, in our case, that it doesn't have the unknown value. And this same idea applies if you are using SQL. Even if your project is written in Python, you may be interacting with a database. And if your data exists in a database, it's going to be much faster just to run these things directly in SQL. So you can also apply these ideas in different languages. Now, I spoke about testing our expectations about the data, but we are also writing code, and we should make sure that our code works as expected. So this is a different type of testing, which is called unit testing. And this scenario happens in our pipeline, assuming we have our data expectations as tests. This happens when data is expected, but the output from our code is incorrect. The idea here is that if we have let's say we have a function that cleans some data, we should break down this big function that performs several operations into smaller functions that have really concrete behaviors so that we can come up with test cases easily. And the idea is that we go from something that is kind of abstract, like has a lot of things going on, to something that is very specific, and we isolate a lot of things, and this makes testing easier. And it's also important to think in terms of what makes a good unit test. You are going to be testing cases that are representative of what you are going to see when you analyze the data. And it's really easy to fall into this trap where you code unit cases that don't make much sense. So I'm going to give an example of how you can think about unit testing. Let's imagine we have a function inside our clean songs function. We have another function that does a count operation. So it's going to count the number of songs for every genre for each user. And this function is called count song genres. And the piece of code that you see on the right is written using the PyTest library, which is a library that I highly recommend for writing unit tests. So we have two tests here. As we can see in the code snippet, we have the complete case. This is a user with ID number 1, and this person has listened to a rock song, a pop song, and a jazz song. So the output is going to be 3 columns, rock, pop, and jazz, and the values are going to be 1, 1, 1. Now, this is a good scenario from someone who's been listening to these 3 genres. Now, it may happen that someone doesn't listen to the 3 genres at all, but we should still be counting correctly. So let's imagine we have another user ID. User ID is number 2, but this person only likes rock and pop. Well, we expect to see the jazz column as output, so that's something that we should be testing. And as you can see in the body of the function, what we are doing is we are calling the function with those 2 input cases, and we are making sure that we have the right set of columns. Now, this is a very simple test, and you could test other things, such as the actual values in the column. But this is the important idea, that you should be testing for concrete things, and also think in terms of scenarios that you should be covering. So now let's speak about a recipe for writing data transformations. And this is a recipe that if you follow step by step is going to help you to write more robust data transformations. Let's imagine we are working on the countSongGenres function. The first thing, even if before we code anything, we just write the name of the function, we write a docstring. And a docstring is just a string that goes right below the name of the function and that explains our purpose for this piece of code. It's basically a justification for why do we have this function. And this is very important not only for other people, but also for you, because like 1 or 2 weeks from now, we are going to forget why you have that piece of code there. So that's step number 1. Step number 2 is to think, what am I expecting about the data? What am I expecting in terms of the input for this function? And we should be writing the data tests, the expectation tests. The third step is to think, what scenarios should my code cover? Which are the cases where the data is expected and I should be operating and applying some transformations? Those are that's kind of the reasoning that you should follow for thinking for good unit test cases. And finally, you code your function, you run your tests, and keep going until all your tests pass. And that's how you make sure that your implementation is correct, at least by taking into account how many scenarios you tested with your integration test and your unit tests. Let's speak about the second challenge, data pipeline structure. Our data analysis goes through several stages that have a predefined order. And this has a really important implication when we are testing code, because it means that any error that happens let's see this pipeline, we have 2 branches for analyzing the user's data and the genres. Let's imagine we are working with the user's data. If we get the data and something bad happens there, all those errors are going to propagate to all the downstream tasks. In this case, all these errors are going to propagate to clean users and potentially even to the code that trains the model. So when we are doing testing, it's very important that we account for this fact. So now let's revisit our idea of data expectations and data testing and turn this into another idea, a very similar idea, which is integration testing. It's the same thing. We are going to make explicit our expectations about the data, but now we are saying how and where we are going to make these tests. And the idea is very simple. You have your pipeline, and then right after you run your task, for example, get users, you test. You run your data expectations. So for every task in your pipeline, you are going to have one function, the function that runs the actual code, and then another function, the function that tests the output, and so that you can explicitly test your expectations about data. Now, if you are analyzing a big data set or any of these tasks takes a lot of time to run, running your integration testing is going to take a lot of time, because that implies running your pipeline from start to finish. And as I mentioned before, speed is very important. So how do we go about that? How do we go about speed? The idea is actually very simple. Since your pipeline operates in many batches of data and applies the same transformations to many rows at once, we can simply pass a sample. And if we pass a smaller amount of data, the pipeline is going to process it in a much faster. So this is a really simple idea, but it implies some work from you, because it means that you have to code your pipeline as a structured chain of transformations, and you have to make sure that your data expectation tests run right after every task. And there are a few tools that you can use. They are called workflow management tools that you can use to turn your code into a pipeline. My recommendation is to use Ploomber, which is a library that I've developed. And it applies this idea, and it allows you to write pipelines very quickly. So that's what you see on the left side. This is one example of how you can develop a pipeline. As you can see, it's just a simple YAML file where you say, The source is going to be this script for get users. And when this task is done, I want to run this function, which is defined in another file. And I'm going to pass one parameter to this function, which is going to be sample. And this is going to allow me to run the entire thing with a sample. And we just repeat the same thing for all the tasks that we have. We say, where's the source code, what function we want to execute when the task finishes. And in this way, we can quickly switch sampling on and off so that when we want to run our integration testing quickly, we just say, run the pipeline with sampling on. And when we want to see the actual output with the full data set, we just turn the sampling off. There are a few other options and things that you can do to speed up your integration testing even more. One great idea is to do incremental builds. Let's say, for example, that in this pipeline, you modify clean users. If you modify clean users, you don't have to run get users again. You also don't have to run get genras or clean genras. You only have to run clean users and train models. So running your integration testing is much faster because you are running fewer tasks. The second idea is to run tasks in parallel. We can see in this pipeline we have two branches that are independent and they meet until you train a model. So you can run these tasks at the same time and you can save a lot of time by doing this. And these ideas are already implemented in Ploomber, so it's very easy for you to get integration testing to speed up really fast. Now let's speak about the last challenge, which is data changes. Even if you are doing all this testing and all these things and you are taking proper care of all these ideas, if the data that you are consuming changes, your pipeline is probably going to break. So we have to think about how do we approach this problem. Well, the first practical thing to notice is that covering all possible input cases is unrealistic. We are not going to cover all possible data input cases because we simply don't have enough time. We cannot just spend all our time testing and not doing the actual work, which is the analysis. So that's a very important thing. My recommendation is to focus on writing data tests because those are really fast to write. You simply have some ideas about the data and you said that you write that in code and it's 1 or 2 lines, it's very easy to write. And if the data tests don't pass, well, you just have to go and revisit your expectations, but this gives you, you are kind of reducing the scope of your code and saying, I only want my code to work under these conditions. So in this way, you are coding simpler functions and you are only gonna increase the complexity if you see something in the data that requires you to do so. This testing trade-off is very important to keep in mind. In one end, you want to be writing a lot of tests so that you can make sure that your data pipeline is robust. On the other hand, you cannot simply keep testing over and over again. And this also has important implications in terms of the nature of data science, because the most important thing when you are working a data science project is to try a lot of things. Ahead of time, you don't know if some pre-processing method is going to work or not. So a lot of the code that you write is not going to end up in production and you are just going to throw it away. So it's not worth your time to test and test and test things that you are not going to use. But there's a trade-off, right? Because what happens if you implement some piece of code that doesn't work, but it doesn't work not because of the actual process, but because you don't implement it correctly. So as you get more experience, you are going to have more confidence in balance this threshold. And it's very important to keep this idea in mind. And the final idea is code reusability. If you have less code, there are fewer things that you have to test. So this is very important. And this has two different implications. The first one is that you should be using other packages. For example, if you are doing machine learning, don't implement your own model. Just use another library like scikit-learn or Keras. And Also keep in mind that you should be using libraries that are maintained, because that's, if you are using libraries that are not longer maintained, that's going to have a whole lot set of different issues. But the second thing also implies that you should reuse not only the code from other packages, but your own code. If you find yourself that you are writing several functions that perform similar things, it's a good idea to write a single function that maybe has some parameters to tweak how it behaves. And in this way, you only have to test a single function as opposed to testing 5 functions that do pretty much the same thing. Now, these are good ideas for development, but when you are going to take your project to production, you have a different set of concerns that you should be aware of. The first important thing is that you should define an unambiguous input schema definition. And this is really just a few data expectations at the beginning of your pipeline, because you are saying, if my pipeline is going to production and I'm going to be making new predictions, I should define what my expectations about the input are. There's no point in running your pipeline if the input doesn't doesn't have this specific format. When you are going to deploy, it's important that you heavily invest in unit testing, because you have to cover more use cases. When you are developing, you can spend more time trying out new experiments and writing data tests. But when you are going to deploy to production, you have to take care that you cover more cases that shouldn't raise errors, for example. And speaking about errors, it's very important that you have good error messages so that you can debug things, and if something goes wrong, you are quickly able to understand what's going on. And related to having good error messages is the idea of logging. If you have good logging, it's going to be easier for you to understand what happened if something breaks. And there's also this idea, data science projects, when they go to production, they usually are deployed either in batch predictions. For example, you make predictions for all your users every month, or as live API where you would have a service that can make predictions on demand for everyone who wants to get a prediction. And for the first case, for the batch case, you are kind of in development mode, right? Because you don't have that pressure. If you make predictions monthly and something goes wrong, well, you can just delay the predictions for 1 or 2 days and fix things. For a live API, the requirements are much strict, because you have to make sure that you get a proper response to whoever is going to consume the service that you are working on. Now let's go to debugging strategy. This is very important, because when you find errors, you have to follow a principled strategy so that you fix the errors and they don't come up again. Let's speak about fixing crashes. What happens when you run your pipeline and it crashes? There are 3 scenarios, and understanding which scenario the case that you are dealing with falls on, you have to do some detective work. The first case is unexpected data, and this happens when you see that one of your data tests crashes. And this is actually a good thing, because it means that you caught something that shouldn't go through your pipeline, that doesn't comply with your data expectations. Then if you find that you are in this case, you either have to relax your data expectations, maybe you have to revisit the definition of your tests, or leave some data out. Maybe you keep, that's for you to decide. Maybe you decide to keep your tests as they are, but in the previous task, you are going to remove some data that shouldn't go through your pipeline. And if you do this, just make sure that you add a comment to explain why you are leaving some observations out from processing. The second case is unexpected data, but when the task crashes, not the data expectation, the code in the task. This implies that you have a missing data test, because the task shouldn't crash if your data is expected, right? So the idea is that you should be adding a data test, then run your pipeline, make sure that your pipeline crashes at that point, and then you're back to case 1. The third case is incorrect code. So again, your task crashes, but it is not computing what you are expecting it to do. So this means that you have a missing unit test. So you should add this unit test see it fail, see that the current implementation does not work, then fix it, run the test, and see that it passes. One important idea that you should keep in mind is that you should be fixing problems in the right place. Imagine that you find your training model procedure is crashing, and maybe it's some of the rows for the users that have some issue which is causing your training model to crash. You might be tempted to apply this fix in your trained model code, but the first question that you should ask yourself is which task is responsible for this output? And maybe you realize that this is really something that clean users should take care of, right? So you shouldn't apply the fix wherever you find it, because you maybe had to fix it in a different place where it is more appropriate to apply the change. And this is important for tasks whose output is used by many other tasks. If you apply the fix in the root cause, in the task that should be responsible for that piece of data, you only have to apply that patch, that fix once, instead of in every task that uses that output. The other scenario, which is harder to fix, are silent bugs. And this usually happens, for example, when you train a model and you realize that it doesn't have the performance that you were expecting, or you compute some summary statistics and the numbers don't make sense. So there's nothing crashes. It's just that our results don't make sense. So this indicates a missing unit or data test. And again, this is some detective work that you have to do to know if it's one case or the other. And to fix these kind of issues, once you find something that doesn't make sense, you should work backwards to find the same idea, right? So who is responsible? Who should be responsible for this piece of data? Then you add the missing unit or data test, depending on the case. And then you apply the same logic that we explained before for fixing crashes. So you basically convert your silent bug in an actual crash, and then you fix it. Now, I presented a lot of ideas, and this slide contains really the most important messages from this talk, and that's what I want you to take away from this. The first important thing is that testing makes reproducibility practical. Unit tests check concrete expected behavior in a unit code, in a piece of code, which is usually a single function. Integration tests check input-output boundaries. So these are the tests that are going to verify that the output from some task is an appropriate input for the next task. You can speed up your integration testing with sampling. You have to be prepared for data changes. You should be writing your tests before you actually write your code, and that you should be fixing bugs in the right place, and you should be asking where it is the best place to fix this thing. Which task should be responsible for this output. Tools and resources. These are the tools that I recommend you to use to start applying these principles. The first one is Ploomber, which is a library that I mentioned before and I'm developing. It allows you to write data pipelines easily, and it has support for integration testing. You can also parameterize your pipeline, so you switch the sampling parameter on and off. You get incremental builds and parallel execution, so you can speed up your integration testing even more. It also integrates with Jupyter, which means you can develop your pipelines in an interactive way. For your unit tests, I recommend you to use PyTest. It's a very powerful library. Spend some time understanding how it works, and you'll be writing very concise, powerful unit tests in no time. Finally, a tool that I recently discovered, NumFOCUS. This library allows you to recreate your virtual environment before you run your tests. And this is great, making dependency installation part of your testing procedure, because sometimes we forget to document dependencies. We just do pip install, but we never keep a record of these things. So if you don't document your dependencies, things may break. So if you are installing your dependencies every time you test, you'll know when these things happened. And finally, some resources. If you want to take a look at the slides, you can get them from there. Any questions, feedback about this talk or Ploomber or anything, reach out via Twitter. I have a blog posts where I explain the same ideas that I talk here and also expand on some other topics that I didn't cover. And finally, I have a code example, which you can take a look to see how all these ideas look in code. And I also set up this example to work with continuous integration. And I want to thank Michael Snow, who provided very valuable feedback to improve this presentation. That's it. Thanks for watching.